Right, well, I am Joshua Krissansen-Totton. I am a PhD student at the University of Washington in Seattle. I'm doing my PhD in, it's a dual title PhD in Earth and Space Sciences and in astrobiology. I'm just visiting Exeter for a few days to give a seminar, and it's been really interesting to me to actually talk to observers and people who are doing things now with exoplanets as opposed to the work that I do, which is more thinking about future observations, because I feel like a lot of the problems that people are having now with observing giant planets are going to be similar to the kinds of problems we're going to have in a few years' time observing these habitable terrestrial planets. So that's part of the motivation for coming here, and it's been really good to get that perspective. So at the moment I am working on biosignatures for exoplanets, basically how do we look for life on planets around other stars. And so that involves things from lots of different disciplines, as you can imagine. Part of it is how are the processes that life does that affects a planet, and particularly a planet's atmosphere, since that's what we can see with telescopes. So trying to create mathematical models of how life might affect a planet's atmosphere. And then it's thinking about, well, how do we detect those signs of life that are produced? Given a telescope, how long do you have to look to see signs of life? And then how do you distinguish those from other kinds of planets that maybe have interesting things going on that have nothing to do with life? So how do you discriminate genuine biosignatures from false positives? How I actually study these things, usually it's computer modeling, right? Because you can't experiment with a planet. Trying to model the chemistry that goes on in the planet's atmosphere, model how life interacts with the planet's atmosphere. But it's not just models that we're making up from nothing, right? These are grounded in what we know about metabolisms on Earth, on the well-tested physics and chemistry of atmospheres. And so these are, at least we hope, somewhat realistic simulations of how life could affect a planet. So biosignatures are important because I think it's one of the most interesting questions you can ask about other planets, or indeed in science in general, right? We'd just like to know if Earth is the only instance of a planet with life, or whether it's a common thing. And so I think it's a motivator behind a lot of astronomy and planetary science that's done. We also want to, even though we can't make these observations yet, these observations are going to be, with future telescopes that are either being built or going to be built soon. We want to start thinking about it now. It's important now because we don't want to get it wrong, right? We don't want to misinterpret something that looks like life, but actually isn't. That'd be bad. And similarly, we don't want to overlook something. We don't want to, have a quick look at a planet, assume that it's nothing interesting going on, but only to miss a biosphere that's quite different to what we expected. So it's important to start thinking about biosignatures now, even though we're not quite at the point where we can do the observations. Well, the next big thing for biosignatures is going to be the James Webb Space Telescope that launches towards the end of next year, 2018. And so, although this telescope isn't purpose-built to look for biosignatures, it's a much more general instrument. It will perhaps be capable of looking for biosignatures around a couple of the very nearest stars. And even then it'll take a lot of effort. It'll take potentially years of accumulating observations until we can really figure out what are the gases in those planets' atmospheres. But potentially this will be our first chance to really check nearby planets for signs of life, and that's going to be really exciting.